Let's go ahead and get started and just continue right where we left off with our really kind of brief time together last Thursday. And I think we talked enough about like hash functions in and of themselves. And so we can really focus today on how one then uses or has historically used hash functions for user passwords. And the big picture and the main takeaway is that one of their intended use cases is to be able to store and check against the output of the hash function when implied in some way, shape, or form to a password versus directly checking a password, versus directly storing a password, and versus directly checking against a password. Instead, since we have this hash function, we know it has some reasonably hand-wavy good properties that if two passwords are different, the output when they're applied through a hash function should also then be significantly different. We can then store just those hash values and not have to worry about storing the actual initial passwords themselves. So in a system, when you try to log in, tells you that your password is wrong, it's probably correct in that sense, but what it's really telling you is as that value that you've entered has a hash function applied to it, the end result of that function is different than the currently stored end result of its own stored hash function itself. Now that's in theory how one applies hash functions to storing and checking passwords. In practice, historically, it's been done not quite in a secure way over time. We'll talk about some of the historical examples of that. So there was this very old, quite defunct network operating system developed by Microsoft and 3Com called LAN Manager or just LANman or just LM. And it is completely defunct at this point, but a lot of the legacy of it still kind of exists in Windows code. So while the term is LM, it really also can refer to kind of early Windows days as well. And there's many legacies of LAN Manager, including things like NetBIOS that we've already talked about. But another legacy of it is the LM hash, which was really one of the first commercial examples of using password hashing algorithms, and really the first one to be used in Windows. So when we look at it at first glance, it'll seem okay, right? It uses cryptographic techniques of the type we know a little bit about. You'll learn a little bit more about when you take 3310. Like most things Microsoft, it is still to this day supported for those backwards compatibility reasons. It is no longer the default choice, the standard choice in any configuration, but it does allow kind of a graceful fallback to NTLM in case other more accepted approaches are not working today. So there's these hash values that wind up being stored, and they're going to be shown, as we'll see here, to be vulnerable for a couple of different reasons, specifically for what we'll refer to as the hash attack, which you did or are in the process of doing as you're finishing up Lab 4, but maybe it wasn't that clear as you were doing it what exactly was happening underneath the hood as you were passing the so-called hash here. This is the original LM hash algorithm. I'm not so certain how much one needs to memorize these steps. I really don't think so. Just being able to read this slide and kind of follow along is probably sufficient, I would say, that we have an appreciation for the kind of things that goes into cryptographic algorithms and resulting implementations. So here are the following steps. So given a user's password, the first thing that happens is it gets converted to all uppercase letters, and it pads to 14 characters. Why 14? Well, we'll talk about it, but this is just a design choice made as part of an exploration of a design space that involved things like performance of the underlying login, maybe some storage requirements, and also the complexity or ability to break into it, as well as possibly reflecting kind of what was known state-of-the-art in terms of cryptanalysis back in that time period. So uppercase letter conversion, pad to 14 characters, split those then 14 characters, of which you'll be guaranteed to have 14 characters, into two halves, each of which are 7 characters long. You then add a parity byte to that. So if it's 7 characters, if it's ASCII, that's 7 bytes. You then add an 8th byte to each, which is just storing parity information, allowing you to determine if any bits got flipped in the middle of some sort of transmission. And then that gives you ultimately what would be referred to in this context as the key, which is a little different than what I introduced and we talked about on last Thursday, where the password would be the message. In this case, just by design, the password winds up being used as the key. So from a certain number of bytes to 14 characters to 16, now split into 2 8-bit chunks, and you wind up with 2 of these 64-bit keys. And so the actual message in this case that gets processed is just a constant string. I tried to look up why this string is this particular string. Seems to be arbitrary, doesn't appear to be anyone's initials, doesn't appear to stand for anything, but it's a little interesting to me. A lot of other approaches may have a constant key and then have the input be what's variable. For this particular approach, the input served as the key, and the thing that gets encrypted winds up being what is fixed here. The end result might wind up being quite similar. You keep one fixed, you keep the other constant. It may not matter all that much, but that is the approach that was taken here using the data encryption standard that would give us then two 8-byte ciphertexts, and then those get concatenated together. Those are what gets stored as the 16-byte value that is the LM hash. Now, just a show of hands, who is familiar with the data encryption standard, or DES? It is old. It is something you will eventually learn as you choose to explore more into this topic. It is old but still taught. I say old but super old but still relevant, like myself, and taught, because it was a very widely used cryptographic cipher. One kind of agreed upon standardized approach to do basic encryption, decryption. So it's considered deprecated, not to be used for new secure applications. But because it was around and prevalent for a matter of decades, it's still seen and used in all sorts of different contexts. Now, I had mentioned how hash functions tend to look a certain way, and they do tend to look a little arbitrary. I take my input, I shift it to the left by 13, I add it to this value, shift it to the right by 7, I do an XOR with the temporary value. Crypto ciphers tend to look kind of like that as well. Although there's a few different things you tend to see in cryptographic ciphers, either from kind of very early standardized ones to ones that are invented today. It is still a lot of just basic arithmetic and logical operations. And there's good mathematical reasoning behind all of that, but things like XOR operations and addition operations, you see that quite a bit. The other thing you tend to see in cryptographic protocols that you don't necessarily see in hash functions would be these kind of S boxes, substitution boxes, and those are lookup tables. Given a byte, treat that as an address, look it up in a table, get a value back out. That's meant to be a way to encode what would otherwise be fairly nonlinear and non-trivial transformations. So our cryptographic cipher tends to look like doing those series of steps a number of times to get some suitably random looking output here. For a couple of reasons, this LM hash approach is not considered an especially secure scheme for storing passwords. Some of the issues with DES were that it's from originally the 1970s with at least originally a relatively small key here. In this case, showing a 56-bit key here. Seems like a lot. 2 to the 56 is, and certainly was, a big number at the time. But there's a big difference between 2 to the 56 and 2 to the 57 or 2 to the 58, right, as you grow your powers of 2. So large, but not insurmountably large. Certainly as we went to the new millennium, it was pretty clearly shown that even 64-bit keys are kind of pushing it, and you really need to move on to 128 beyond. That is specific issues with DES as a choice. Even if DES had a little bit of more strong key strength to it, just the scheme itself has some fundamental limitations. And part of this analysis is really just advanced counting of the type that maybe you do not in a digital logic, but in a methods class, discrete math class. In this case, if it was 14 characters was the limit of a password, it was actually limited first off to the printable ASCII characters, so it's less than it seems at first glance. It gets split by design into 2 separate halves, and 2 7-bit quantities is significantly different than 1 14-bit quantities in terms of the permutations that corresponds to, right? The enumerations that are possible. One is 95 to the 14, the other is 2 times 95 to the 7, which is a significantly smaller and different number. And then even from within this ASCII space, if everything does get converted to uppercase, that lowers that value quite a bit less as well. And you may say, 7.5 trillion is a big number. It is to you or me. We couldn't count to that number. We have trouble visualizing such numbers, but now we're well within the range of what modern computers can at least attempt to enumerate through. So conceptually, some of these things are okay. Using an older cipher, was a reasonable choice at the time and only less reasonable as time progressed. But some of these decisions result in what appears to be a long password, in fact, being treated as two relatively short, relatively limited passwords with a resulting space that, given a fast computer, you can enumerate through all the possibilities and determine whether or not there is a match or not. So if you were wondering why, as you were working on Lab 4, we were doing some unpacking of a stored hash into a potential password, why that password was in all capitalization. We had to figure out a different approach to actually find out what the actual password was. It was because it was using a variant of this algorithm here, which as part of the storage approach converts everything to uppercase first. So in terms of reversing that, you wind up with a result that's in all uppercase. The actual password itself would then be some variant of that. But keep in mind, let's say a 10-byte, 10-character password, you get it and it's all entirely in uppercase. There's only so many permutations of what the password can then be, right? If I forget what it was, oh nuts or something like that was the password from the lab. That was 6 characters or something like that it was being used. Well, each of those bytes could independently be uppercase or lowercase. That's only 64 possibilities one has to explore. You try all 64, you'll determine which one was the actual password. Other approach with both LM as well as NTLM. Well, first off, in terms of what NTLM changed, is it was arguably a more straightforward, more sensible approach, which was just to run the password through a hash function. Also an older hash function, but at the time certainly considered valid. That is to say, this prior approach, if we go back to this, is a lot of seemingly work to get a result that is effectively a hash function output. And then recognizing that that is ultimately what's getting generated here, the NTLM improvement variant of it was just to take that password and run it through a hash function that is in fact better in some sense, but it does not take advantage of the common practice known as salting, which we did look at in the lab, but again, there was just one step where you kind of just combine the salt value with the password value and maybe just kind of directly did it. This is an important topic to kind of discuss sort of briefly here. So ignoring this bottom half for now of this diagram, what we've been talking about so far is taking an input password, applying a hash function, MD4, MD5, even that Jenkins hash we looked at before, and then storing that hash function somewhere. The issue with just doing that is that the hash function that gets stored for a particular password is going to be exactly the same in any system or configuration that uses that same hash function. You type in your password, 12345, it applies MD4 hash to it. What gets stored on that particular system that is calculating and storing that hash would be the same exact hash value that would get stored on any other system for which anyone used the password 12345. And maybe we can think about why that would potentially be an issue, right? That as soon as that hash value is then discovered because one particular machine is vulnerable, it would then turn out that anybody else who used that same exact password, whether it was you or whether it was a different account, but presumably for yourself, there's a potential reuse of passwords on any other machine that used the same hashing algorithm, and here we're talking all Windows machines here, would have the same exact stored value on all of those other machines. So we'll talk a little bit about this concept of pass the hash. That was more also of an implementation detail where just the hash itself could be sent versus just attempting to send the password in the first place. But it enables this kind of hash reuse, which would be considered sort of an insecure practice. That the hash itself is not necessarily a secret. It has to be stored on the systems you're authenticating against. So if we lose kind of the confidentiality of that hash, and it's the same value for that same password used on any machine, we lose potential confidential access to all of those machines. So this now common practice of salting, the idea is we're adding something extra. some extra effectively random, and it turns out it doesn't matter what it is as long as it's reasonably long and reasonably random. We're adding some extra random data to the end of the password before hashing. And as I mentioned, that's the exact goal of it, that each machine, presumably also each user for that machine, would have both a password as well as these extra random bytes that get generated, and those are what get stored together. So in some sense, it's taking your password, which may be a good password, may not be a good password, and it, in some sense, makes it a better password because it's just adding extra randomized bytes to it that you don't even necessarily know what they are, nor do you need to know what they are. So now when we apply the hash function, this is meant to be like a concatenation symbol here. We take the input password, we take the actual salt value, we concatenate them together, then we apply our hash function. We have to store then both that stored hash as well as that randomly generated stored salt value there. In some sense, the password is still the same as what it was before, but now the advantage we have here is because the salt values are stored, and because now they're randomized, they'll be different on one machine to the next. They'll presumably also be different from one account to the next, even on the same machine. If you have the hash value that's stored on one particular machine for one particular user, it doesn't give you nearly enough information to be able to determine what the hash would be on a completely different machine. Your password may be 7 characters, it may be 12 characters, 14, something in that range. The salt value can be as large as it needs to be. It's just getting randomly generated. Nobody has to memorize those values. And so you're getting from your relatively small, not unique password, a relatively long, relatively unique password that can be stored differently on different machines. Questions about salting our passwords? It's very common practice now. So as I previously mentioned, actual password is not what gets stored, right? It's the hash that gets stored, as well as the salt, if that salting approach is used as it is commonly used. By consequence, this is both, it's kind of a good and a bad thing in some sense here. By consequence, the actual password that gets entered doesn't have to match what the intended password was. In fact, because the intended password never really gets stored, we don't necessarily even know what the intended password was. The entered password doesn't have to match the intended password. Only the resulting hash value needs to match. And there's some consequences of that. In one sense, it's a good thing. Well, I'm never storing the passwords themselves anywhere. That's one less thing I have to worry about losing somewhere along the line. That's a good thing, I guess. On the flip side, we have to have these hash values be accessible somewhere in the system. Once I have access to these listing of hash values, and presumably I also know what hashing approach was used, and there's only a handful that we would want to potentially consider, we can keep just generating password/hash combinations until we find one that matches. We do a little bit of that in Lab 4 as well. The math for this gets bad pretty quickly to our advantage, right? If you think of each character in a password being a byte or being 8 bits here, each time you add an additional byte to your password, you're multiplying the complexity by 2 to the 8, right, by 256. You can do just some of those quick numbers in your head if you want to. If you have 10 characters, that's 2 to the 80 possible passwords one would have to enumerate to have a very high likelihood of matching the hash that you have stored for you. And that's still, even today, a pretty big number to kind of enumerate through. So that approach, while there's still some value to it, is usually kind of the backup worst case scenario approach if someone's trying to figure out your password or gain access on a system. We usually don't do that. The term you may hear that referred to is sort of brute forcing a password, and there's just limits to how well that can actually be applied in practice. The numbers grow very quickly. I say here, very slow, that's certainly true. Likely to get noticed and or locked out. Well, that may be true, but that's, if we have the hash values, we can do this offline. We don't have to keep attempting re-authentication in a brute force manner. That would get noticed very quickly. Another competing approach, which is worth talking about, although we won't really dive into algorithmically why this necessarily works. But the alternative of sort of brute forcing something computationally, which is I'm going to try password 0000, then 0001, etc., and enumerate through all of them until I potentially get a match. The alternative to that is to pre-compute every possible hash in advance and store the corresponding password entry. Now, I have an asterisk here. I added that this morning. This is not strictly true. It's close enough to true. That idea of pre-computing every possible hash and storing it in a table alongside the corresponding password that would have led to such a hash, that's known as a hash table. People use the two terms hash table and rainbow table interchangeably. One is a special case of the other, and they're very similar in terms of what they're doing, but they're not exactly the same thing, hence the asterisk that I added here. But the hash table concept kind of makes some sense, right? There's only going to be so many things I want to consider. Perhaps I don't do every possible password, but I do the top 100,000 most common passwords. I then store the corresponding hash value for those 100,000 most common passwords. I do that all in advance. Now when it comes time to determine whether I can break someone's password, I first look it up in that hash table and say, yeah, it's there. They used a commonly known password. The rainbow table takes that approach and kind of applies effectively what is a compression to that approach. And the idea here is that we do something, we start very similarly, right? We start with passwords, we apply our hash functions to possible enumerated passwords, but then we also then alternate converting it back to a string, rehashing, converting it back to a string, and applying basically a hashing chain to a potential password. This isn't on the slide, you'll have to take my word for it or look it up elsewhere. And that chain can be pretty long. It could be a 10 hash entry chain, it could be 100, it could be 100,000 as well. When we then get a new hash value that we want to see if it's in the table, we then apply that same chain, that same exact combination of hash and string conversion functions to that hash value as it comes in, and see if at any point in that chain does it match in our resulting hash table. If it does, we still don't know the password, but we can kind of reverse engineer what the password could have been by starting over and going back to where we had that exact match there. That is effectively a type of compression where we can't enumerate all the possible values, right? 2 to the 80 grows very big very quickly, right? But we can encode a lot more potential passwords in each entry in a rainbow table, maybe 10, maybe 100, maybe 100,000 entries, by just storing the final result and not storing all the intermediate results. So it is, in some sense, a type of compression. And that was needed as a practical matter because those tables will grow very quickly, very large, very quickly here. The resulting table can get quite massive. This is just a online rainbow table size calculator. I can zoom in a little bit here. We'll still have to fix the projector one of these days here. And in this case, we're saying it's an arbitrary hash function. The actual hash function doesn't matter in this case. It's just telling you how big the table would need to be. 4 potential password character sets, in this case, A through Z, lowercase, uppercase, and then the values 0 through 9. For a password length of 1 to 7, with a little bit of calculation of what the likelihood of a match would be in that particular table. Somewhere here there needs to be a number of steps applied here. Chain length of 10,000. This would say how large the table needs to be. And here we're really talking more about storage and computation. And it's really big. That is with the kind of compressed by a factor of 10,000 approach here of a rainbow table versus a hash table. In some sense, this is just spreadsheet math again here, right? You have so many bits of your possible password. You want to store all the possible hash values. Effectively, we're taking that result and dividing it by 10,000 when we use a rainbow table, this rainbow table. That's the resulting storage of that. Doesn't take too much for this to grow out of control. Because you may say, well, that's large, but I have a nice big hard drive. It stores terabytes of data, perhaps. All I have to do is do things like, let's now add additional symbols, right? So add expected things people want in passwords. For various reasons, we don't often want things like quotes and brackets and passwords, but you do see some systems that use it. Spaces are also not that common, but sometimes you see spaces and passwords as well. So we can do all 19 characters in the set here. Those are your printable ASCII characters. And now we say, instead of passwords that go to length 7, let's have a more reasonable policy. Let's have passwords of length 14. Any guesses as to how big this rainbow table would need to be then? We've blown it up quite a bit, right? We went from the base being, I don't remember if this was 62 characters, so 8 times 62 in terms of, the bits of storage. So that went from 62 to 95. That's a pretty big explosion in and of itself. We went from 7 to 14 characters. Each of those would be multiplying by 250, well, no, not by 256, but by those 95 possibilities. So a pretty large space it would be multiplying by. I can't do that math in my head. I don't have to. The spreadsheet does it for me. And the result is NA. So let's give it to a number that it can actually calculate. And okay, I hadn't tried it before. With 12 length characters of that character set of size 95, we now require 8,000 exabytes, which there's some data warehouses that can store those things, but I'm guessing you don't have access to any of them. So at some point, the rainbow table itself becomes a little bit impractical. I should be able to say, let's make longer chain lengths. I haven't explored that. That should be basically dividing the number by 10 each time I add another 10 of the chain length. And so maybe if you have a sufficiently long chain, you're getting to some reasonable storage. But while this is an interesting approach to kind of store more than just the raw hash values here, and it is an interesting kind of compression technique, there's still just some fundamental limits of, for a given password complexity and password length, what the resulting table size would need to be to have stored an entry that corresponds to your password. And it becomes a probabilistic thing, right, that you get some certain confidence value for a certain size password. This is to some extent the reason why when you go to a new service and it asks you to generate a new password for it, that it has all sorts of kind of Byzantine rules about it must not, or must include uppercase and lowercase and some special characters and numbers 1, 2, and 3. That is part of the reason those rules are in place. They're not explicitly to make rainbow tables less impractical, but that's a nice side effect of those sort of policies. What is a more common approach to cracking passwords is to recognize that, well, as humans, we are oftentimes kind of limited in terms of the passwords that we generate ourselves. If you use a password generator, you're probably in better shape. But if we ourselves are picking our own passwords, we do things like reusing passwords. We do things like using names and phrases and other kind of information that can be used to deduce passwords. So what is a more common approach is to instead take a database of common passwords. Also, you can think of them as known bad passwords. If it's a common password, it is a bad password. And to store just those values in your hash table or in your rainbow table. Again, it's a probabilistic kind of approach. Maybe that catches 40% of the passwords that you're interested in cracking. That's still pretty good, right? For a relatively small amount of storage. You may want to check out those links. If you go to the slides, you can view those links. A known password hash combo sort of public table. This is listed as really bad passwords with the unsalted MD5 hashes. I don't want to scroll here because there's some like inappropriate passwords that are in the known list of well, we're all adults here, but I don't want to scroll by it anyway, that are on this list. But these are just examples of common password or known bad password database, what the unsalted MD5 hash would correspond to for those passwords. So it turns out having just 0 be your password is a bad password. Likewise, 1, 2, 3, 4, 5 works well for luggage, not well for securing access to computing systems. And you may think you're clever by going all the way 1, 2, 3, 4, 5, 6, 7, 8, 9. That's also in this database. It turns out not to be a good password for that purpose. This is really nothing clever about it. This is a hash table, right? This is for a list of chosen passwords. The list can be as long as you have time and storage to compute and store the results, what the resulting value would be in an unsalted password storage, unsalted password file for that. So we'll try 12345. I don't recall if this password lookup uses MD5 or SHA-1. Probably tries both. See, it says it tries LM, NTLM, MD4, MT5, SHA-1, so it'll work with all of these things. And you should be able to take any of these values, put it in there, click that you are not a robot, assuming you're not a robot. I don't know if you can see that's very tiny even on my screen. You see that it is able to look up that hash value in the rainbow table, get the resulting password back out for that. Another possible action item for you would be to check any of your passwords if they show up in this list. You may want to change it for that purpose or not. Perhaps the best security is having the weakest possible password. What do these storage of passwords look like in practice? It's very operating system dependent. In Linux, typically by default these days, there's the /etc/shadow file, which stores the usernames and hash values. There's a separate /etc/password file, which, despite what the name suggests, usually is not used anymore to store the actual passwords, but it does store things like user IDs and group IDs and some sort of permission set associated with that as well. So oftentimes you would have both of those files as part of your password cracking strategy. That is what we do in Lab4. There's a command which is really something you could have written yourself called unshadow that takes this file, takes the password file, and just kind of concatenates them together. So it's something we could have just written ourselves. This is the /etc/shadow file that stores both the salt and hash values themselves. Just a pretty quick breakdown of what's in it. I mean, some of it we can kind of see, the rest you really can't tell just by looking at what's stored in that particular file. There's the username is stored. The actual hashing method that is used with these days, I believe this is still correct, SHA-512, used by default here. The salt value, that's going to get randomly generated on a per user or per account, per machine basis. Then the actual computed hash value here, and then some other password-related metadata that can be useful. When was the password last changed? The minimum password age, the maximum password age. All of those values, because this is sort of the Linux philosophy, we want everything, at least historically, to be stored in a human-readable file. That's becoming less and less the case these days, but certainly historically that was kind of one of the design philosophies. As part of that philosophy, there has to be an agreed upon way to take what is otherwise arbitrarily random binary data and store it such that it can be human readable. And that's why these hash and salt values do look human readable. It's because they're encoded in a mechanism referred to as base 64, which is used for all sorts of different purposes, but this is one common use of it. And it's almost like a reverse ASCII encoding. It's not quite that, but it's almost along those lines, in which the idea is we have this binary data, right? Now the salt need not necessarily be binary data, but certainly the hash is just going to be randomized looking data, right? Zeros and ones in random combinations of a particular, in this case, 512-bit length. If I were to just take a random 512-bit string and try to store it in a file, you would have all sorts of things that don't fit within those 95 characters of the ASCII set that are human readable. You'll get a lot of weird binary looking blobs. Depending on your editor, maybe you'll be able to see them all, maybe you won't. In a hex editor, you'd be able to see them all, but in terms of human readable format, it wouldn't really work. And so for this, in other contexts, when we want to effectively store binary data in a way that you can still read it as a human, we use things like base 64 encoding. And the idea there is you have this binary string. Think of your 512-bit binary string, which is the SHA-512 hash function output. In this case now, we're doing what I'm kind of referring to as like a reverse ASCII character. In ASCII, we have these bytes, and we choose to interpret each byte value as being a different character. Some are readable, some are not. things like line breaks, carriage returns, null bytes. There's an ASCII byte that's supposed to play a little like tone in your terminal when you print out that particular byte. Here now we have an arbitrary binary string, and we want to convert it to something that is going to be guaranteed to be human readable. So there's just an agreed upon RFC, agreed upon standard here, where what we do is we take this arbitrary binary string as input, we then just chop it up 6 bytes at a time. And you may say 6 is kind of a weird number. We usually chop things up, did I say 6 bytes? 6 bits at a time. We usually chop things up 8 bits or 1 byte at a time. In this case, though, the goal is to convert everything back to something that is human readable, and 6 bits is a good choice. That gives us 64 human readable characters. That gives us A through Z, uppercase, lowercase, that's 52, plus 0 through 9, that's another 10, plus 2 other characters that we have here as part of the 64 possibilities that we're encoding here. So we take our input, we split it up 6 bits at a time, and then we just convert it to the corresponding character. So going back to that example of our shadow file salt value, there's this random thing that gets generated on a per account, per machine basis that's getting concatenated with our password before the hash function gets applied to it. And while it is kind of tedious, we can look at that salt value and say exactly what that binary string happened to be. It's YZJ, all caps to start with. So the actual values that are getting computed are 011000, 011001, followed by 001001. And we can reconstruct the entire binary string via that basis. Same for the result of the hash function as well. It's encoded in a similar way. This, which looks like an arbitrary number of values, it's like some 80-some readable values here, is actually a 512-bit string just re-encoded into base 64. So what is in our password file or our shadow file? It is a version of exactly what we've been talking about. User has a password. We don't want to store the password. We instead want to apply a hash function to that password, but not just the hash function to the password. We want to store the hash function to a password, plus some extra random stuff to kind of make each hash value unique, even for the same password. We store both that unique information, that salt information. We then also store the resulting hash value. When a user types in their password, we take the password, we combine it with that stored salt value, we recompute the hash, and we then do a comparison whether it matches this particular 512-bit string. That is how we do modern password authentication, at least with basic password authentication systems. In Windows, it's effectively the same thing. These examples I grabbed because it does make our life a lot easier in lab. These examples, and they're stored in their own Windows-specific locations, which are effectively the same as an etc/password or shadow file. In this case, these are both examples of unsalted hashes, but the concept is very similar. I don't annotate it the same way. Username, aspects that relate to user account permissions. So for administrator, you see 500. That tells you something about what that user has access to. In this case, both the old school LM hash using the DES function to generate a cryptographic output, as well as the NTLM using MD4, and just storing both those things also as those base 64 values. In this case, these are stored as hex values in our SAM file here. It's different. It's not that different than what we're seeing here. It's just a slightly different way of encoding the value, slightly different way of storing multiple possibilities here, not so dissimilar in terms of the approaches that are being used here. Questions about password storage and hashing? I want to reiterate my goal, right, which is as you're doing things like using John the Ripper to do password cracking, you type in a command, it does work, but I think it's important to appreciate what is actually what is really happening underneath the hood. Whether we truly understand it at being able to read the source code and kind of reverse engineer the exact approach used, we at least need to gain an appreciation for the broad strokes of what is happening. This topic that we're on is escalation and exfiltration. We were talking more about, in this case, kind of lateral movement on a machine, which is I already have some access to the machine. So consequently, the assumption we're starting with here is that we have some access to the hash file on that machine. And in both Windows and Linux, somewhat by necessity, regular users have to have some sort of access to these files. That's not always the case, but it's a common assumption that holds true, and it holds true in our lab configuration as well. So our assumption when we talk about lateral movement on a particular machine is we already have access to the machine. So we did the prior lab 3 and earlier techniques, and we now have some sort of shell or some sort of access to the particular machine. And then now the assumption going forward is we also then have access to those hash information as well. With that information, we can now start to, in practice, apply these both hash table, rainbow table type attacks, as well as a more sophisticated kind of reverse engineering of the password attacks. When we use this John the Ripper, I say great software, amazing logo. The software's been around for a very long time. And it can handle a lot of the different hashing approaches and attempt different things to attempt to reverse engineer what the password is. Starting off, and we did exactly effectively this in lab, right? Want to unshadow the file, meaning concatenate user information with the stored salt and hash values so that it's just one big file. And then the command is just called John. In this case, we're going to be passing it a word list, which I don't specify what it is here. And we're going to attempt to crack the values that are stored here. And John will attempt to be relatively efficient. It's not telling us that all that much. That remember, we saw this in the shadow file. So it's, in this case, the type of hashing is option 1, which happens to be MD5 with 128-bit output. This is telling me that it's using SSE2 because there's certain instructions on this particular processor that are going to be efficient and effective in calculating a lot of hash values quickly. And it's going to attempt some multi-threaded approach to do the hashing. This is a result of a screenshot of it in progress and not completely done. But John is going to try different things depending on what you specify, or depending on, from an easier to harder or less painful to more painful kind of strategy that it does take. Has a default order of modes, which you can then tweak and customize to yourself. The default order, the first thing it very much wants to try is to start with a word list file or a password list type of file. The idea being that a lot of passwords are known or bad passwords, and people, when they're asked to specify a password, don't just randomly mash the keyboard. They try to pick something that they can remember that may be based on commonly known words. So the word list mode would start with a file, like a text file, specifying here's a list of possible words to start with to consider as possible passwords, as well as some basic so-called mangling rules associated with it. So when I say, for example, password as spelled accordingly, the idea being that people also tend to, in practice, take things that would be letters in a password corresponding to a word, and they convert it to things like special characters or numbers, and they do some capitalization and lowercase manipulation. All of that sounds good in terms of adding security to your password, but if we think about it in terms of like this binary arithmetic, right? Well, again, we already talked about that. Going from uppercase to lowercase for each individual character kind of doubles the complexity of your password. That's just one extra thing I have to try for a particular byte in your password. Likewise, it may seem clever to take a 0 or take an O in your password and convert it to a 0, but there's only so many permutations there that kind of make sense as well. So this is the default thing that it starts with. Given a list of words, try them, try kind of obvious mangling and permutations of those. The word lists themselves can start from relatively small word lists. You can find word lists available for purchase that are growing into hundreds of megabytes to even larger word lists. Here's one that shows there's a zip archive, and this is what it uncompresses to, roughly 610 megabytes of text words. That's a lot of words. I mean, it's kind of hard to reason about like what that means in terms of like a dictionary. 610 megabytes, each byte corresponding to one character in each word. let's say roughly 6 bytes per word. Um, this is rough. Roughly 100 million words in that particular database there. That's a lot of words. In common English, we don't use anything more than a number, just a few thousand number of words. You look at kind of all written English in common usage, it still just grows to tens of thousands of words. We actually don't use all that many words in practice, and they can grow extremely long. These password lists. Um, I did click this. I don't recommend it, but all-in-one password list, which is 329 gigabytes once uncompressed, and just available for you to download or torrent quickly. Um, some of these things are already kind of pre-doing the mangling and manipulation of the word list. That's how you get to such massive amounts. There's only so many permutations of ASCII values that would correspond to words. So it's not just dictionary words at this point. Once you get to hundreds of megabytes and gigabytes, it's also some of those manipulations already in place. We start with a reasonable word list in lab. The lab is designed such that reasonable word list is sufficient for our purposes. But as you may have experienced in Lab 4, it does take a little while to crack all those passwords, and you're supposed to be patient and wait for it to complete. In practice, though, you really don't know how long it would take to complete, because that is the word list approach. It's certainly not, this is all probabilistic, right? It's certainly not guaranteed to be successful. Other things that John the Ripper would also then try is referred to as single crack mode, which is it maybe a really bad password? Is it some manipulation of the username or other login information? If I were to choose this is my password, this would be a bad password, and I'd have to do something else in order to secure my accounts. And then after it's trying, kind of dictionary or massive dictionary lookup, and then kind of ultra clever, kind of trying to determine really simple things, then it effectively then goes to the brute force mode. And the tool will tell you when it's gotten to this point. That doesn't mean it's a bad thing, but now we're getting into that enumeration of our large binary space where you have to tell it either give it some reasonable restriction, which is try all passwords of less than or equal to 6 or 7 or maybe 8 characters, or you just have to manually stop it yourself, because this as an enumeration approach, which is just try 0000, try 00001. It's effectively doing that, right? You can maybe start to measure its performance in terms of doing those password generations and cracking attempts, but it could be exceptionally long in terms of how long it takes. You give it some limits, some guardrails, or you just stop it, or you just let it run because you have a computer that you don't need to crack anytime soon. You let it run for months. And then separately, it also has a plugin architecture that if you have your own concepts of what the passwords could be or suggestions for how best to approach a particular search, you can then write your own plugins so that you can have it do the search yourself. What we've been doing beyond just playing around with John the Ripper is we've been doing the so-called classic pass, the hash attack. And as I mentioned, that one of the strengths, also maybe one of the weaknesses of Windows historically, is this kind of reliance on backwards compatibility. So even though we have the landman operating system that is that's from the 1980s, is completely defunct, and we have hashing algorithms that are effectively, provenly bad to use in common day for backwards compatibility reasons, while by default nobody's attempting to use NTLM for password security in modern Windows systems. If a client says, I'm not capable of using Kerberos, for example, it will attempt to then fall back to those older, less secure approaches here. When using the NTLM authentication, it actually just sends the password, the hash of the password, directly over the wire without any encryption or anything like that. That is a separate vulnerability in the approach as well. So you don't actually need the password. The password itself is never actually sent, but the actual hash value, such as what was stored in those files, is just getting directly sent over the wire in any authentication attempt. So assuming one can capture those hash values, we do it kind of manually via, like a Metasploit shell where we grab those values and we copy paste them into a file. We could also have done so via just basic network sniffing as well. We can just take those values and use it to log on to a separate machine that is following a similar authentication scheme. And by design, Windows comes with all sorts of utilities that sort of make having a reverse shell not that necessary. So psexec is basically sort of a Windows telnet application that still is available for just remote administration, remote running of processes on other Windows machines. It's kind of a a precursor to PowerShell, but also with fewer of the guardrails that PowerShell already has in place. So once you have the hash from one machine and it's using this NTLM with no salting involved, you now have access, if that user has the same password on other machines, to be able to run arbitrary code on those particular machines. Let's leave things right there for today. We'll finish this up on Thursday also, and then we'll jump into the next topic, which is looking at web security. Thank you.